Okay, we have three examples here. I only wrote one formula. I would always provide this on my exams for integrating inverse trig, or we will get a result of an inverse trig. So you've done derivatives of inverse trig, and we can verify that in fact, if you do the derivative of the right-hand side, you will get this, right? And um, the u's or x's or t's, whatever the variable is, we always have chain rule. So we're going to try to manipulate these integrals to look something like this, or we might in fact end up using the derivative as well, like we will in this first example. Okay, so these are beyond the basics, right? This is after you've had some examples and you understand how to manipulate the formulas, uh, probably, towards the end of this lesson. So let's get going here. The first one. First off, I mean, it looks hideous, right? And often, like so far, what we've seen is make u just the ugly part of the function, make u the denominator to try to get du over u. And sometimes, like, it's just a matter of guessing and checking to cut down some time and not sit here and guess. I kind of thought about this problem before I started the video, and we're going to make this u. Okay, that is the ugly part, so technically, I mean, I am totally following one of the rules. Like, I don't want to mess with that tan inverse with the integral in there. I don't recall a formula. I'm sure there is one because there are millions of formulas out there for integration. But let's get going. Let's make that u. Then its derivative, I mean, based on the formula we have on the right here, right? Like the derivative is 1 over, well, okay, du over a squared plus u squared, right? So du, chain rule. Why do we have du? That's because of the chain rule. I know I'm saying u is this whole thing, so maybe it'd even be better to call this v. So by chain rule, I need dv over a squared plus v squared, right? Because I already used du up. So the chain rule says 2t, but then the derivative of tan inverse is 1 over a plus u squared, a squared plus u squared. So 1 plus t squared squared. Well, that's great, because notice t squared squared is t to the fourth, so I have everything I need with the exception of a 2. So let's go ahead and rewrite this problem to kind of clean this up a bit. T times tan inverse t squared, oops, give myself a little bit more room, tan inverse of t squared dt all over 1 plus t to the fourth. Oh, and I'm so bad at this side. Remember when you do u du, we're taking it with respect to t, right? And therefore, to see what du is, the way I like to do, and there are other ways to do this, but I just move dt to the other side, okay? So 2t dt. This becomes increasingly more important as you move forward in calc. Okay, this lesson typically is a Calc 1 lesson, but it's very important to keep our all our variables straight. Okay, everything straight. All right. So I'm missing a 2. And any constant is easy to manipulate because I didn't change the problem at all by doing what I just did. Right? 1/2 times 2 is 1. If I'm multiplying by a form of 1, constants can go outside the integram, then I didn't change the problem. So now let's look at what we have. Tan inverse t squared. This piece here, we called it u. Everything else I had in green here, 2t dt, right? 2t dt was part of du, and the 1 plus t fourth, all of that stuff is du. Now it's important you don't end with a divide by du, right? You need, du is always in the numerator, it's always multiply, just like that formula that we had manipulated for this problem. We have u du. Now in a roundabout way, so 1/2, I made all my substitutions. We actually aren't integrating a form of du over a squared plus u squared, but we needed that in order to create our u substitution, right? We actually needed the derivative of tan inverse, which derivative of inverse trig functions came long before integrals. So we integrate this, u squared over 2 plus c, never forget your constant, which therefore we get 1/4, right? 1/2 times that divide 2, 1/2 times, I just said 1/4. 1/2 times 1/2 is 1/4. And back substitute u, right? We have u squared, but u was tan inverse of t squared, and then squared plus c. Okay, that is all u, right? U squared. And that's the answer. As ugly looking as that thing is, that's all we can do. All right. Next one. Again, we're trying to find u du and ln squared t. Like, I do see this t in the denominator. That's a good sign. But if I made u, like often we shoot for the ugly part, right? 1 plus ln squared t. Well, ln squared t means ln t squared. So if we were to do du, we would have 2 ln t multiplied by 1 over t, and that's close, right? I needed this 1 over t dt, but I don't really know what to do with that. I can't just add an ln t here and then divide, because now I don't have u du or anything, so that's not going to work. What we can do, though, is a simple manipulation of the formula that we were given, and say, all right, well, if u is just ln t, then I have this a squared plus u squared, right? And du would be dt over t, and that works perfect. Let me change the color here. Du equals dt over t. So now I can look at this and say, all right, I have du, awesome. So integral du, and in the denominator, I have 1 plus u squared, right? ln is u, and this is u squared. Perfect. Now that matches the formula we had at the beginning, where a is 1. U we already said, right? It's ln t. So just plug everything in. So we have 1. I'm going to go ahead and write the ones, but just to show we did, in fact, find what our a is. U is ln t over 1 plus c. So rewriting that, we have tan inverse of ln t plus c. All right, no further simplifying there. Okay, last one, we have a definite integral, and cosine tan inverse t dt 1 plus t squared. Okay. Notice this is here, right? And kind of like the first one, we're like, well, make that u. I have du. If u is tan inverse of t, then my du, just trying to get colors straight here, is 1 over, or sorry, dt over 1 plus t squared. which is here. There's du. And then I have cosine u, right? So cosine u du. dt over 1 plus t squared all became du. And the integral of cosine is sine. Now, changing your bounds, that's completely up to you. It wouldn't save a whole lot of time in this one, so I'm going to skip that part. Normally, I would change these, right? Like if t is 0, then what is u, right? If t is 1/2, then what is u? Also, looking at this one, I'm like, well, I don't want to change the bounds because this would say tan inverse 0. That's fine. We could do that. But what is the tan inverse of 1/2 for the upper bound? Right, this one. I don't know. Can't really do anything with that. Like, no matter how you do it, you're going to have to evaluate this in some way. So it doesn't really matter. I guess it's all preference. So moving forward. Integral of cosine, we know is sine. Now, it's sine of u, though, so we need to go back and plug in u, right? If I'm not changing the bounds, I need to go back and plug what u actually is. So to evaluate this, either draw your triangle or use Pythagorean identities, substitute it, I mean, however you want to do it. Okay, many approaches. I'm going to just take the approach, I'm going to plug in 1/2. So I have sine tan inverse of 1/2 minus sine tan inverse of 0. Okay, tan inverse of 0 we could do, that's on the unit circle. So what angle would give me tangent 0? That's 0. So remember, your inverse is giving you a theta. It's giving you an angle. So we have sine 0. But tan, where is tangent equal to 1/2? That doesn't happen. Remember, all of your points consist of, like, the first one at pi over 6 is root 3 over 2 1/2. And tangent's y over x. There's no way that's going to manipulate to 1/2. So therefore, how I prefer to do this is to draw a triangle. Remember, I'm getting theta is 1/2 for tangent. So I'd have a triangle whose tangent, opposite over adjacent, gives me 1 over 2. Now I need the sine of that angle theta. So sine is opposite over hypotenuse. Well, using Pythag, we could see the hypotenuse is square root of 5. So therefore, the sine of theta, opposite over hypotenuse, is 1 over root 5. And sine of 0 we know is 0 because sine is the y value. So therefore, we get 1 over root 5, or multiply by the conjugate to simplify. I'm going to leave it at that. Looks good enough to me. Notice if you had changed your bounds, you would have done this step here anyways, and then we still would have this result.